Hi guys, welcome to Chemistry Lesson 6.06 over molecular geometry. We're going to be talking about something that scientists call Vesper Theory, V-S-E-P-R, and it's pronounced Vesper. And it stands for, you don't need to know what it stands for, excuse me, but in reality it stands for Valence Shell Electron Pair Repulsion Theory. And it describes the molecular geometry or the arrangement of bonds and atoms in 3 dimensions. So remember, bonds are shared pairs of electrons. So if we have a bond, we have a shared pair of electrons. And electrons have negative charges. In science, one of our rules is that opposites attract and like charges repel. So if you look at this molecule, for all of these diagrams, let's talk about these symbols a little bit. Every atom usually has a central, every molecule has a central atom, and so A is our central atom. And a bond indicates a sigma bond. A pair like this indicates a lone pair. So for this molecule, here I have A is my central atom, and then I have, let's see, X would be outlying atoms. I have a central atom A, and I have 2 outlying atoms X, and I have a sigma bond here and a sigma bond here. These electrons want to get as far away from each other as they can. And so what will happen is this molecule will orient itself, if you can't read this, along a 180-degree line for maximum separation. I said this is a sigma bond and that's a sigma bond. When a molecule has that arrangement, we call that linear. So any molecule that has that arrangement is linear. So if I look at my central atom and there's 2 sigma bonds, and remember there's going to probably be more bonds in the terms of pi bonds, but we're going to ignore pi bonds. So for all of these, we ignore pi bonds. Well, it makes sense. So here we go. I have my central atom, and I have 3 outliers. So I have, 3 bonding pairs. To get maximum separation, these are going to have angles of 120 degrees. So if you looked at this molecule, I don't know if it's recording these flashes or not, but if you looked at this molecule, you would see that it looked a little bit like a fidget spinner where the 3 bonds would orient in a plane out from the central atom. And so we call this geometry trigonal planar. Now notice my hybridization here. With 2 sigma bonds, this is going to be an sp hybridization. With 3 sigma bonds, this is going to be sp2 hybridization. Well, what if instead of, here I have 3 sigma bonds, so this was 3 sigmas. Remember, that's the symbol for sigma. Over here, I have 2 sigma bonds and 1 lone pair. Well, it turns out that lone pairs are more repulsive than bonded pairs. Lone pairs are more repulsive than bonded pairs. So here's my lone pair, and here's a sigma bond, and here's a sigma bond. And you'll notice here it says less than 120 degrees. This lone pair, instead of having 120, 120, 120, this lone pair is going to push these two bonds closer together. And this bond angle, the angle between these two bonds, is going to be a little bit less than 120 degrees. So these are going to be a little bit more than 120 degrees. Overall, the geometry of this molecule is going to be bent. They also use the word angular. I don't see that very often. We're just going to call this bent. This is also going to be sp2 hybridization, because remember, to count up our hybridization, we look at the bonds and we look at the lone pairs. So this would be 3 hybridized orbitals for sp2. Okay, if we go to the next line and we look at this geometry that's called tetrahedral, we have tetrahedral. You'll notice some odd sketching. So what we have here, I'm going to re-sketch this. We have A, and then we have in a straight line coming up, we have X, and at 120, we have X. But then really close to each other, we have this wedge here. It has an X, and we've got a dash wedge that says X. This is trying to show us a 3D drawing. So this is going out of the into the paper. This is coming out of the paper, and these are on the plane of the paper. But if we could measure the angle, so we've got, let's look at all of our angles here. I've got angle 1, I've got angle 2, angle 3, angle 4, and I could do then angles between this X and so on and so forth. If I took any of these angles, what I would find is that all of these angles are going to be 109 degrees apart. But it's tough because we're trying to draw it on 2D paper. So this type of a diagram shows this bond's coming out of the paper and that bond's going into the paper. This is how we try to draw bonds in 3D, even when we don't have 3D. So if I have 4 sigma pairs, I should have done orange. So here I have 4 sigma bonds. All those bonds will orient in space at 109 degrees apart. And we call that arrangement tetrahedral. Well, our hybridization, I've got 4 hybrid orbitals. So this, and actually everything on this line, is going to be sp3 hybridization. Well, for the next box, I have 3 sigma bonds and I have 1 lone pair. And notice this says less than 109 degrees. So these are going to have a less than 109 degrees, and these are going to have more than 109 degrees because the lone pair is more repulsive than the bonded pairs. And so it's going to tend to kind of push down these bonds. We call this geometry trigonal pyramidal. Trigonal pyramidal. Finally, here I have 2 sigma bonds and I have 2 lone pair. So here's my sigma bonds, here's my lone pairs, and there's a double arrow for much less than 109 degrees. And again, this is going to be the same as this. We're going to have the same kind of angle here, and we call this bent. Well, on a test, how are you going to know what these geometries are? You have to memorize them. Now, the good news is we could look at the next line down. If I have 5 outliers, I'm going to have 3 of them are going to be on a plane. They're going to have 120. The 2 are going to lie above the planes at 90 degrees. That's trigonal bipyramidal. If I replace that with a single pair, then I get a sawhorse or a seesaw. If I get 2 lone pairs, that's T-shaped. And here I'm going to have linear. We're not going to really see these. We're keeping our Lewis structures here and above. We're keeping them pretty simple. I think. I don't know. We might get a couple of these. Not many, though. So for test time, what you'll have to do, where'd my big Sharpie go? Seems to be gone. Let me get my red marker back out. So this line, everything above this line has to be memorized. So you have to memorize these 6 geometries, and they're the most common. So what are our takeaways? We're looking at the actual molecular geometry. So in the past, when you draw an atom, I told you guys it really doesn't matter how you draw it. You might have drawn, your nitrogen, your ammonia like this. But what we see is that actually what's going to happen is that ammonia is going to have a trigonal pyramidal. And now when we draw ammonia, we know that it should look like this. And that it has a trigonal pyramidal arrangement. So what we're doing is we're trying to figure out what the actual arrangement in space is of these molecules. And it depends if they're all sigma bonds or if they have lone pairs, because the lone pairs are more repulsive. So they push on those sigma bonds a little bit more. If we have all sigma bonds, we get equal distribution. So in linear, we have 180 degrees, trigonal planar, we have 120, tetrahedral, we have 109. You don't need to know those bond angles, but you just, you need to know that they're equal here. But over here, when you get a lone pair, you end up, if you have 2 lone pair here or 1 here, you get a bent. And if you have 1 lone pair and 3 sigma bonds, your trigonal pyramidal. So in the last video for this chapter, we're going to practice drawing the Lewis structure, determining the molecular geometry, and the hybridization. And we're just going to do about 2 or 3 sample problems where we're doing all of that. So in case you're wondering why we don't have sample problems in this video, it's because we're going to practice in the next video. All right, that's all for now. Thanks for watching.